Okay, so as we saw, there's a huge difference between planets and stars. Okay, and the main thing that we saw and concluded in the last chapter that planetary formation is a natural process from star formation. Okay, and before we used to assume that, you know, planets were rare, but now we're finding that they're not, that typically any star that's forming will also create stars and planets in the process. So this is a big conclusion. So now what we want to try to take a look at is stars and how stars form and the entire lifetime of stars. So we want to first start with the basics of stars, like what is a star? How do we differentiate them from planets? And how many different types of stars out there? There's so many. So you could literally get a nice big list of all these different types of stars, and we're still finding these exotic type stars and giving them names out there. So most stars are pretty well documented and we understand their life cycle, but there's some real stragglers out there, outliers that are very different, and we're trying to understand them. Okay, the big things we want to look at is like for the birth, lifetime from birth through the life of the star to its death. The death of stars is really fascinating. That's where we get into black holes, because there's a certain type of star death that results in a black hole. And we'll look at that towards the end of chapter 11. And, you know, we know that lots of these stars have planets around them. And we want to think about the statement too, we're all made of stardust, right? You might have heard that one. It's very popular. And it's true. All the exploding stars out there are making all the materials that make life as we know it, all the heavy metals and everything else that we see. So literally we're made out of supernova, which is exploding star material. So some fascinating topics to address here. Okay, so let's take a look at some ideas here. So there's so many different types of stars, and I want to start grappling with all these labels. And in our classification of stars, we'll have a small group of labels that we want to be familiar with. Okay, so some of these stars that you'll hear of are blue stars, blue supergiants, red supergiants like Betelgeuse, yellow dwarfs, orange dwarfs, brown dwarfs, T-Tauri stars, Wolf-Rayet stars, white dwarfs, neutron stars, magnetars, and on and on and on. There's so many. So we're going to define a small class of them and look at the typical stars in a star's evolution, the typical labels we see in a standard evolution scheme of a star, lifetime of a star. Okay, so all stars share the same attribute, which they all start from a cloud of gas. They're born out of the different nebula. Okay, so, and we know that this results in planet formation via the solar nebula theory. And the big difference is stars are so much more massive than planets, right? So we have this cloud of gas that compresses, you know, the gravity starts acting on this cloud of gas, and that makes the star and all the debris from that star turn out to be the planets. Okay, and the big thing is stars are so much more massive that is what distinguishes them from planets. They got so much mass that nuclear reactions begin in that star. So you're squeezing all these kilograms together. So you're squeezing all the stuff together, and as in that process, that creates the habitat to have nuclear reactions occur. That's where you start getting the hydrogen atoms slamming it together to create the helium atoms and the energy that results. So the nuclear fusion process is big for a star. Now, there are some stars out there like the brown dwarfs, which are considered stars by most academic astronomy circles. And they don't quite have the same nuclear fusion process as the other stars. They create something called deuterium instead. but they're very low. They're the lowest mass stars on the spectrum. But that's sort of the exception to the rule. The rest of them fuse hydrogen into helium, and then they go up the chain. They start fusing some other higher, heavier elements as they progress. So we'll look at a little bit of those ideas towards the end of the chapter 9 through 11 material that we're hitting. Okay, so when the fusion no longer occurs, then the star begins to die. So even though that some of these stars no longer fuse hydrogen to helium or some of these other atoms, we still will call them stars. Like we'll call a white dwarf a star because we know it's in its dying process. We know that's the dying ember of a star. So some of that language could get a little confusing, but again, that's the number one feature that we distinguish is the mass is so huge that we have these nuclear reactions going on. Okay, so the main component is hydrogen, but as we'll see, there's different types. Some of the larger mass stars will burn heavier and heavier elements up the periodic table. And we'll look at some of these different types of stars and how they evolve. So one of the main ideas that the key thread in all these chapters 9, 10, and 11 is how you live your life as a star is dictated by your mass. How much mass you have at the beginning of your life, how much mass you have at the middle, and how much mass you have at the end tells you a lot about how you're going to have your lifetime, how you're going to live your life as a star, how you're going to die, how you're going to evolve, etc., how you're going to burn your fuel. So that's really a big property to understand as far as classifying stars. Okay, whoa. So we talked about distance before, so we're going to get back to this. Distance idea. So you want to review some of your light year lingo. So it's going to be helpful because the final is coming up. And other distance measures that we use. But instead of just measuring distances around the solar system, like in AU, astronomical units, now we're really getting to the light years and the parsecs measurements that we use. So the two main distances are the light year, okay, and we know that's how much distance is covered by light as it's traveling the speed of light, okay. And so we have a light year conversion here. That's so many meters times 9.46 times 10 to the 15 meters. That's a lot. And then we have a parsec. And parsec is based on the angular measures of the sky. So you could break up the whole sky into 360 degrees. Okay. And if you do that, because it's a sphere around us, it's a circle. A sphere is three-dimensional circle. So we break those up into little sections. We break them up into degrees, 360 degrees. Each degree contains 60 minutes in it. And we could even break that further. We could break each minute down to 60 arc seconds. Okay. And that's a measure that's used. So we could break the sections of the sky into these tiny pieces called arc seconds. And when we're talking about the sizes of stars out there, they're really tiny. We're talking about our arc second sizes, okay? Really, really tiny dots in the sky. So we take that measure in arc seconds and we could figure out how far away it is in parsecs, and we could convert parsecs to light years. So we talk about parsecs in the sense that it's the mean radius of the Earth orbit that's extended at an angle of 1 arc second. So what we look at is we look at the radius and we break up that circular measure right here into 1 arc minute, into one degree, into 60 arc minutes, into 60 arc seconds. Okay, so we could get this tiny, tiny little measurement that will allow us to find the distance. So here's a formula that's going to come up, and this is a good practice for you to understand how to go from these measurements of arc seconds in the sky, which is what we typically use for stars, and relate it to parsecs, how far away it is as far as distance. So little d stands for distance here. So your distance in parsecs is equal to 1 divided by lowercase p, which is your arc second value. And that comes from something called parallax. Okay, so we'll take a look at that. So here's a very important formula for doing those conversions. You have some of those on your worksheet. And I'll post an example too as well. I have one on here. So moving on with this idea, we're going to relate this to a concept called parallax. Okay, so what happens is this is your angle. This P is your parallax angle, and that's measured in arc seconds. Okay, and here's your distance. Let's say we're measuring a distance to a nearby star. This D is in parsecs. So here's your distance in parsecs. Here's your parallax angle in arc seconds. And you could again replace using this formula. When we're measuring this parallax angle, we're measuring it with this average AU distance between the sun and the earth. Okay, a lot of times we'll measure this angle from one point of our orbit. Let's say we're going to take this measurement of a star. We're going to measure this angle of this star with respect to the background stars, let's say in June. Then 6 months later, we'll orbit and we'll come on the other side of the sun. And then we'll measure this parallax angle with respect to these background stars. Okay, so taking these parallax angle measures is tedious work, and we have satellites that do that for us, that are constantly measuring how much this nearby star moves with respect to these background stars. So that's a phenomenon called parallax. So trying to give you some a little bit of a foundation for that formula, understanding how that formula, where that formula stems from. So this idea of parallax is the difference in apparent position of an object when you're viewing it along different lines of sight, perspective shift. So that's just parallax in general. So stellar parallax is when we're measuring these star distances via small shifts in a star's positions caused by the Earth's motion. So if you're on this side of the Earth, you're going to see this star in front of these background stars. And then 6 months later, you're going to see this star against these background stars. So that's what we mean by it appearing to shift against the background stars. So I'm going to take a moment here. I'm going to stop sharing. And I'm going to have you do a little experiment. So this is how you do parallax. So every astronomy student has to do this at least once. Okay, so you get your finger out in front of you. Okay, and then pick an object in the room. Like let's say you have a picture on the wall or a clock. So I'm going to put mine on clock. So put your finger maybe centered on that object. Okay, and look at it with both eyes. Now what you want to do is cover your left eye and look at your finger in front of the background object. Then cover your right eye and keep your left eye open, and you'll see that your finger has moved with respect to the background object you're using. Does anybody do that and see? Okay, so put your finger in front of an object, keep both eyes open. Okay, close one eye and look at your finger in front of the object. Then open that eye and close the other and see how that background object, how your finger has seemed to change its position with respect to the background object. That's how you can see parallax at work. Okay, so try that little experiment. It's a really fun experiment. I have a little parallax and angular measure supplement I put on post on our website. You could read through that, and that has a little bit more details. And we typically do that as a lab experiment. So I'm going to get back to sharing this. So that's the big idea. So some of these simulations that I have to show this is right here. Okay, so here we have Earth going around the sun, and I've made the inclination angle 0 degrees, meaning we're looking at it head on as opposed to at a 35-degree angle. So we're just tilting the orbital axis if we want to, but either way, it's not going to change. So if we keep this edge on like this, we could see how changing the distance, here's your parallax angle, and that's 0.50 arc seconds right here, okay? So you could find the distance using distance equals 1 over p by saying distance will be 1 over this 0.5, and you'll get 2 parsecs out of that. So if we shorten the distance, you'll see how the angle changes. You're going to get a bigger angle. Okay, so at 1 parsec, you have an angle 1 degree. And if we measured something that at 1.67 arc seconds, 1.67, we'll get like 0.6 parsec distance out of that. Yeah, so it's a really interesting way to look at this. And here's another way of looking at it. So as we're going around the sun, here's our nearby star. So maybe we're looking at Proxima Centauri or some other nearby star, and we're measuring it. We're measuring this angle. Okay, we're measuring this angle it creates with the background star at 2 different orbits of the Earth. And we get the parallax angle in arc seconds, and we can use that formula to find the approximate distance. So one other thing to come up with is this is how we measure arc seconds as well. You could actually measure these angles, these angular measures. So this gives you a relationship between your distance, and this number comes from some your radian measures. So it's not important that you know all that, but you could read through what I have as far as my supplement goes if you want to explore more on how we actually get the angular measures. Because one of the things we do in astronomy is we use degree measures to estimate the sizes of objects. So if you were going to estimate the size of the moon, I'm going to bring this up to the supplement because I think this is an important topic. Hang on, I'll have a lot of, there we go. So this is a supplement that's up on our page for this week's module. And that goes through a lot of these relationships. You could just explore it loosely, so I'm not going to hold you responsible for all these details. But one of the things we do in astronomy is we approximate angular sizes, and we have these approximate angular size measures we could do with our fingers. Okay, so 1 degree is like your measure of, like, let's say your pinky, about. Or some people could even measure their index finger to be about 1 degree. So if you could cover up the moon with your finger, you know that the moon is less than 1 degree in size, and which is true because it's about 1/2 degree. The moon and the sun are both 1/2 degree in size. These are just ways of estimating objects in the sky. So if you're like measuring the comet tail too, let's say you're doing your observational assignment, and it stretches across your whole fist like that, you could, or about across 3 fingers, you could say it's about 5 degrees long or about 10 degrees long. This is an estimate that astronomers use as far as sizes in the sky go, and it's related to the arc seconds because, again, here's 1 degree, and if we break that 1 degree down into 60 units, that would be 60 minutes make up that degree, which is also 3,600 arc seconds that make up that degree. So that's a really small section of sky we're looking at when we're taking these angular measures of stars and then equating it to their distance in parsecs. Okay, let's move on here. All right, so you could go to those simulations that I have, and they're also listed. There's one listed here. Okay, so here's a typical calculation you should be able to do. And this is the one from your worksheet, so you could check your work on that. Try to do it on your own first, and then see if you could get it. So here we have a star. Let's say we have data from one of our satellites, and it says this star has a parallax angle of 0.24 arc seconds. What's its distance? Well, the distance in parsecs will just be 1 over p, this measure in arc seconds. So 1 over 0.24 gives us 4.17 PC parsecs. And recall from our measurements earlier that parsecs, 1 parsec is 3.26 light years. So we can convert a parsec to light years. And by doing my parsec conversion here, I cancel out the parsecs and I get the light years. I get about 13.6 light years as the distance. Okay. Now you could also go the other way. If you know the observed distance, let's say you know something's 250 light years from the sun, you could find the parallax angle. It's just the opposite. The only difference is you'll have P here equal to 1 over D. So in this case, what I want to first do, if I have a measurement in light years, I want to make sure I convert it to parsec, because again, this formula only relates parsecs and arc seconds. So here what you want to do is, let's get rid of the light years. We know 1 parsec is the same as 3.26 light years. So I'm going to get rid of my light years. So I divide out the light years, and then I get 76.7 parsecs. And then the next step there is to plug those values in to this formula right here. Okay, and I get 0.013 arc seconds, which is a really tiny measurement in the sky. Hence, this is why we really rely on our satellites to take these measurements for us. And the Sloan Digital Sky Survey is constantly mapping all these stars and these distances. And we also have the Hippocrates satellite that's also doing it. There's a few missions that are out there doing these tedious measures. So make sure you practice that. The next thing we want to look at was star basics. So we have all these different types of stars, and we want to understand these star distances. But the big one that's already come to our attention earlier when we're just observing the night sky and trying to understand the cycles and patterns is this idea of magnitude. And magnitude is nothing but brightness. Okay, so you could think of apparent magnitude as observed brightness, and absolute magnitude is like absolute brightness. When we put all the stars at the same distance, that's how we compare the brightness. But when we just look up at the night sky, we know that we want to have some catalog of saying which objects are brighter than others. And the magnitude scale, as we know from the previous chapter, was adopted from the early Greeks. And so we know the lower the value, the higher the magnitude is. So we have negative values for magnitude, and the more negative it is, the brighter it is, appears to us. So apparent magnitude is just look at everything. We don't care about the distance, and this is how we're going to compare what we see as far as brightness goes. But then the absolute magnitude is, let's put all these objects at the same distance and compare the brightness. Okay, so just some review here on the magnitudes. I started with that because that's what we're familiar with. So we know that the sun has apparent magnitude that's very high, negative 26.7, the brightest object in our sky, correct? But its absolute magnitude is just 4.8. That's very dim. So if we put the sun out there in the sky further away, it would be hard to see, very hard to see. So this gives you some comparison. And we know Sirius, which is deemed the brightest object in the night sky, Sirius, which we'll see, is actually a system of stars. It's a binary star system. Its apparent magnitude is negative 1.46. Okay, but it has an absolute magnitude that's positive. So if we put the same distance with other stars, it would actually be dimmer than Rigel or Betelgeuse or Deneb. So this really kind of helps you to understand how it would look if we were paired up at the same distance with these other stars. Okay, and here this gives you an idea of the distance here. And we know distance really impacts a brightness, but we'll also see that there's other factors that impact the light that we see. The size, for instance, is going to be a big factor. Okay, so this also gives you the parallax angle, and you could play around with that formula, and you could find, using this arc second and parallax, you could get that parsec measure, and vice versa. You could get this parsec. If you have this parsec measure, you could get the arc second measure. So I'm going to add a few new terms here that come into play. And again, we're not going to go through this rigorously, but this is really, a lot of this language gets mixed up when you're talking about stars. There's this idea of flux that comes up, and we use it in relation to understanding something called luminosity, which is what we're really interested in as far as classifying stars. Now, flux is when we look at how much energy is coming out of the surface of an object, we call that flux. So if you draw all these little lines coming out of an object's surface, right, and you call those photons, if you're going to count all the photons crossing over the surface of the star, we would call that flux. Okay, and there's a standard formula for flux, which is this constant called sigma times temperature to the fourth power. And this value sigma, this constant, is so many watts per meter squared times Kelvin to the fourth. So it tells you watts is a measure of power, which is energy, how much energy emits over a period of time. So what you really just need to know is this basic definition: amount of energy that comes out of the surface in a certain amount of time. Okay, and that's the actual relationship. Flux is sigma times 10 to the times temperature to the fourth power. And we use flux to understand luminosity. So taking it one step further, something that's a lot more formal than just magnitude and brightness is understanding the luminosity of a star. Now, luminosity is a measure of that light energy that depends on the flux, the temperature, and the size. So luminosity is going to be the flux times the surface area of the star. So this is really important. So here we're talking about luminosity is how much energy is coming out of the surface in a small amount of time times the actual surface area of the star. So that means the bigger the star is, the bigger ball of a star it is, the more surface area it has, the more luminous it will be. So important detail. So we could see stars that are larger further away because they're a lot more luminous. So some stars are really, really far out, but we could see them because they have such a large surface area. Okay, so we'll come back to these ideas. So this formula is inserted right here. Okay, so this will give you a little picture too. So if we have, here's a star and it's emitting all these photons, and if we take a little section, we'll say, here's how much energy is crossing this little surface. But if we take the whole surface area, then we'll get the luminosity. And the surface area of a sphere is 4 times pi times the radius squared. So what we do is we use radius values to talk about the size of the stars. We talk about how big the star is from the center to the edge of its sphere. and that's the radius. Now, what we do with a lot of stars and in comparing other stars with their own sun's evolution is we use our own sun statistics to compare other stars with. So we all say like this star is twice the size of our sun, so it's 2 solar radii in size. Or we'll say this star is 4 times the mass of the sun, so it's 4 solar masses. Or we'll say this other star is 10 times as luminous as the sun, so we'll say it's 10 luminosities, stellar luminosities. So we use these sun comparisons, these base units to compare other stars with. So that's why I had you write these down in your worksheet, and they're good reference points. Probably another one to put in here is the sun's temperature, because sometimes they even compare the sun's temperature. They'll say it's twice the temperature of the sun. And we use, again, that as a base unit. But just to understand how this works, I give you a challenge problem. And I just want you to understand the trends and not necessarily the numbers. Not like the parsec and arcsecond formula. That one you should be able to compute. But for flux and luminosity, a computation that can be done with those formulas. I'll just do a little pause here. We have a little phone ringing break. Okay, so if we look at this, here's a good example. So here we have Betelgeuse, right? 640 light years away, and Betelgeuse is in Orion. It's the red giant that is theorized to go supernova, explode soon. And it has a surface temperature of only 3,500 Kelvin. So as you hopefully remember, the sun's surface temperature is close to 6,000 Kelvin, 5,800 Kelvin. So this is a lot lower temperature, hence the redder light. However, it's huge. It's 887 times the radius of the sun. So that means 887 times this number right here. Okay, 887 solar radii. So if we wanted to look at the flux, we'd say this is the symbol we use for flux is equal to this constant, this sigma, times the temperature to the 4th power. So we would put that constant in there, times it by 3,500 Kelvin to the 4th power, and this is how many watts of flux it has. 8.6 times 10 to the 6 watts per meter squared. Now, to get a better picture of this is to understand its luminosity. So the luminosity of Betelgeuse would be the surface area 4 times pi times its radius squared times the flux. So when we do that, it's 4 pi times 887 solar radius value squared, and I would put this number in here, times the flux value found in the previous step, and I get 4.12 times 10 to the 31 watts. Okay, now that's the luminosity of Betelgeuse. So this is how many watts it's putting off. That's a lot of 100-watt light bulb. So if you divide by 100, you would find out how many 100-watt light bulbs that is equivalent to. Very, very bright. Okay, so this compared to the sun, which is times 10 to the 26 watts, is huge. So the reason Betelgeuse is so much more luminous is not because its temperature here, that does play a role, is because its size is huge. So, and the idea is the bigger light bulb you have, the brighter you're gonna be, right? So very important detail there. So that's what I really wanted to highlight is this relationship here. Even though it's a smaller temperature than the sun, it still is more luminous because of its size. Okay, so here's some other luminosity trends. It's kind of putting it together, some things to think about, because this is what astronomers had to puzzle out over the years to be able to classify stars and compare them. So we know that if we, what happens to the star's luminosity if you increase the temperature? So going back to that formula, it increases to the 4th power. So if you had something that was 2 times the temperature of the sun, its luminosity would increase by a factor of 2 to the 4th power. It'll be 16 times more luminous. Okay. So, you know, we could have the sun on one side and this other star that's twice the temperature. Let's say they're the same size, assuming they're the same size. And we would say it would be 16 times more luminous than our actual sun, just based on that temperature. So what happens to a star's luminosity if you increase the size? If we increase it by, it increases by a square factor. So if we double the size of our sun, it will increase the luminosity by 2 to the 2nd power, 4 times more luminous. Okay, 4 times more energy output. So luminous is a more formal term than brighter. We don't want to just say brighter, we want to say luminous, because that means so many watts over the surface area, how much energy output it's actually creating. Okay, but the observed brightness, so what we will see is a difference in this brightness. If we were trying to look at the magnitude scale, we know that as you, here's some general trends, as you increase the distance, things will dim. There is a relationship between the distance and the brightness as you observe. So the observed brightness will, your brightness reduces by the inverse square. So what that means is that as your distance increases, you square that distance in the denominator and it will be much dimmer. So here's an example. So if you're twice as far, you'll be 4 times dimmer. If you're 3 times as far, you'll be 9 times dimmer, etc. If you are 4 times as far, you'll be 16 times dimmer. So here's a little illustration on how that works as well. Okay, so hopefully that helps to distinguish between the language that is used, and gets confused a lot of times when we're talking about the energy output of a sun and what we see as far as how much light it's putting out. Okay, so the next thing we want to talk about is mass, because as I mentioned earlier at the very beginning, mass is what tells you everything about the evolution of the star. It will dictate how it will burn its fuel in its core, how it will live its life, how it will die, etc. So how do we determine mass? So I'm not going to go through this in extreme detail. Your book has a lot of wonderful details on binary star systems. So what we're in understanding mass from binary star systems, trying to figure out how many kilograms the star has can be a daunting task, right? We can't just go over there and out in the cosmos and put a star on a scale. It's just not going to work. So you have to think about, like, how in the world can we figure out how heavy those objects are? How many kilograms those stars pack? Well, the key is applying Kepler's law of planetary motions, the periods, the law of periods, and looking at the law of gravity, Newton's laws of gravity and his laws of motion. So using those laws, we can actually tease out what a star mass is via looking at star systems that contain at least 2 stars. If we have 2 stars, we could see how they orbit each other. We could look at the orbital motion. And by looking at that orbital motion, how they're moving around this thing called the center of mass, we can understand how much mass there is by doing the calculations. So we look at binary star systems to figure out these masses. So the 2 stars, a binary star is 2 stars that orbit around a mutual center of mass. And it's just like the Earth-Moon system, right? So we say that the moon is falling towards the Earth, but the Earth is also falling towards the moon. But the formal way of stating that is to say the Earth, moon are orbiting around a center of mass. The center of mass is if you took all the kilograms between the Earth-Moon system and at their distances and you computed where the average should be. And it's actually right on the surface of the Earth, the center of mass of the Earth-Moon system. So binary stars behave the same way. It's not that one star is orbiting the other star, it's that they're both orbiting around the central mass point when you add all the kilograms of both those stars and factor out their distances. They orbit around something called the center of mass. And by looking at that orbital motion in the period of rotation, we could figure out what each star's mass must be approximate to. So some really clever techniques have been developed to do that. So we have lots of different binary systems, and Sirius used to be thought of as one star, and until we got better telescopes, we were finally able to decipher the fact that these two stars in this diagram, Sirius A and Sirius B, are not just one star, they're actually two different stars. Okay, we could resolve the star so that we see those two stars. And this is a type of binary called a visual binary, where we can actually see that there's more than one star with better resolution, better scopes. These other methods, so the other method here is a spectroscope method, and this is where we use the Doppler shift. We see two stars that appear as one, but what happens is, so this is really hard to visually resolve with the telescope, but what we see is that if they're aligned correctly, right, we could have one star pulling one way in redshift and we'll see a blue shift in the other direction. So we'll see a blue shift from one star and we'll see a red shift from the other star. Then they'll move around and rotate, and then we'll see the opposite happening for each stars. So I'll show you how that works on a little diagram coming up. And this eclipsing binary system is when you have one that crosses in front of the other star and dims it, just like we were looking at as far as the transit method when we're looking for exoplanet. When a planet crosses in front of its host star, it actually dims the light and produces a light curve. Well, the same thing here happens too. If we have two stars orbiting the center of mass, we could have one that passes in front of the other, eclipses it and dims it, and then it passes in front, and then the other star, then it brightens again. And these create these light curves, and we look at these Doppler shifts and then use that to find the period and then finally the mass. So there's a good website here that I have a link to, and I'm going to bring this up because I really, if you wanted to look more at these binary star systems, this is one of the best resources online for them. And you could get into a lot of detail. So here they talk about Alpha Centauri A and B. That's another visual binary system. And that, you know, they take a look at these and they plot the periods, and from the periods they deduce the mass. But here's a good visual on the spectroscopic binaries. So here you're looking at, here you have your two stars A and B. Okay, so you're seeing no Doppler shift in the spectrum of light. So here we're looking at the light spectra that's being emitted by the stars, and there's no Doppler shift. But in this case, in this setup where you have one moving away, star B is moving away, star A is moving towards you. As you move towards you, the light is being blue shifted. So you can see these lines blue shifted. As you're moving away, these lines are being red shifted. So you see both a red shift and a blue shift occurring. Okay, so those Doppler shifts will give us enough information to produce velocity curves, which will then give us enough information to figure out what the mass is. Okay, I'll bring that point up when we look at galaxies, because the same thing is going to apply for galaxies. How fast galaxies are moving around the center will tell us the mass of the galaxy. And galaxies are groupings of stars, as we'll see in chapter 12. So that gets into how those that system works. And then we have eclipsing binaries. It has a little more detail here. And these are the typical light curves that you'll see produced. And then you have some other techniques being used for binary star systems, but we really like binary star systems because it is our big clues to how we actually find the mass. Okay, so I have that link set up here. And let's go back to our slides. All right, so you might want to go back to some of the spectra stuff, our slides, and I'll bring that up possibly tomorrow, but so you could just review. So the main thing here is temperature. Temperature is another important factor in classifying stars, just like masses. Okay, but really the mass, how heavy it is, really dictates how hot it's going to be as well. So really important relationships. The Stefan-Boltzmann law, we haven't talked about it, but it's another, it's related to the luminosity, but it just says that hotter objects will emit more light at all wavelengths. So this will give you the amount of watts, energy, powers, energy per unit time, and it's based on the radius of the star and the temperature of the star. So you don't need to know that formula, but just know that this is the basic idea behind the Stefan-Boltzmann law, which is what we use to really understand star temperatures. And then we looked before at Wien's law, which talked about, you know, the hotter the object is, the higher frequency light it'll emit, right? There's a direct relationship between the temperature of a black body, and assuming that more stars are acting like black body, and the light that it emits. So we talked about if you heat anything up to a certain temperature, it will produce it'll produce peak wavelengths. It'll produce the most amount of photons in a certain color of light. Okay, so really important law here too as well. So you might want to review some of Wien's law. So some ideas to think about here: as you increase the mass of the star, the radius and the temperature increases to make more energy to hold that star up against gravity. And we'll talk about hydrostatic equilibrium, which is a process that the light pressure, the radiation pressure from the star, is held up against gravity. Okay, so some of these terms can get really detailed, but so we're going to start with the basics. We'll look at a little bit of the nuclear processes, but nothing too formal here. Okay, so these ideas are really important because we've had this historical way of classifying stars that we still use and can use for the majority of the stars. Like and I need to point out that there's still some outliers out there. We're finding some really exotic stars, but most of the stars we could classify using their spectral types and this HR diagram that we'll talk about. So we classify stars by their surface temperature using letters of the alphabet. And we have 7 main types of stars that are denoted in order of decreasing temperatures. So O stars are the hottest types of stars. And then we have B stars, A stars, F stars, G stars. The sun is a G25 star, which we'll talk about. The sun is in this category. K stars and M stars. So one way you might want to remember this is only bright astrophysicists fight green killer Martians. But there's so many other mnemonics out there. But that's a way of remembering the classification of stars by their temperature. Now, what we're going to see is that these spectral types are graphed horizontally in this HR diagram. And it shows the relationship to their luminosity based on their temperature. So some thoughts to think about: if 2 stars have the same temperature, but one has the largest radius, the larger radius star is more luminous. So just remembering what we were going through before, that makes sense. Luminosity depends on radius and surface temperature. So this will give you some, this is what we're going to look at in a nutshell. And we'll have to learn some of our star terms because this comes up in the HR diagram. So this is how we're going to mainly classify stars: mass, temperature, luminosity. These terms come up a lot. So here's the O-type stars. Okay, so we're talking about this temperature range, 40,000 Kelvin. That's huge. So the radius, you know, we're talking about larger radius type stars and luminosities. Here we have B stars, 20,000 Kelvin. A stars, 8,500. F stars, G stars, and then we go up. We have several steps from 5,700. So we'll look at how in the entire range for G stars. Okay. So I'm going to bring out my notes here. There's a range of temperatures associated with each of these. So O stars really, I might have to edit this a little bit, because O stars, depending on where you look, O stars are really generally believed as 30,000 Kelvin and above. B stars are really from 10 to 30,000. So this is the average. This looks like they've averaged the temperatures here. Okay, so I'm going to come back to that because I have another classification that comes up here, and I'll give you some range of figures. So just note that there's a range of figures associated with each of these spectral types: O stars, B stars, A stars, F stars, G stars, K stars, M stars. Okay, so before we go a little bit more into this HR diagram and classifying stars, just to understand some of these terms, because this is brought up right away, so it's probably good to understand some of the lingo here. So just to get by with our classification for now, you want to be familiar with the most common types. So we have T Tauri stars. A little pause here. Okay, T Tauri stars. These are stars in the beginning stages before fusion. So we talked about the sun in the previous chapter when we're looking at the solar nebula theory and the evolution of our sun. It started as, with the birth of our solar system, it started as a T Tauri star, and then the fusion occurs. So we usually call these are just from the protostar becomes a T Tauri star, and then it fuses. Okay, then we have main sequence stars. This term is going to come up a lot. These are, we'll talk about low to intermediate mass range. We're going to have different ranges of mass for stars. So our sun is in that category. We're in the medium. And they've begun nuclear fusion. They fuse hydrogen into helium, and they exist in the state of something called hydrostatic equilibrium, which is where the light pressure holds up against gravity. And stars spend about 90% of their lifetime in this stage. So majority of stars are found here, and they spend 90% of their life there. So this is where our sun is right now. We're a main sequence star, and we have a long time to go in that main sequence stage before we actually run out of fuel. Okay, so we'll talk, we'll compare this when we look at the evolution chains of stars. Red giant stars, these are low to intermediate mass range, but these are the stars that have run out of hydrogen in their core to fuse, and they leave the main sequence. So this is our future. We're going to eventually become a red giant. They start expanding due to what happens is they run out of fuel and they start bloating. They get this radiation pressure that exists because they start burning these shells. So we'll talk a little bit about the shell burning. So this red giant stage is what's in store for us. So this happens to low intermediate sized stars that have left the main sequence. Now, white dwarfs are the dying embers of low to medium mass stars. So what happens is eventually you'll go from a red giant and you'll expel your atmosphere and you'll become a white dwarf star. Okay, and white dwarfs, the fusion is no longer occurring, but the surface of the star is still held up. through this something called electron degeneracy pressure. So it's this repulsion of the electrons that's holding up against gravity. So when we talk about star deaths, we'll understand a little bit more what happens to, you know, other stars that can't do this anymore. So there's quite a few different scenarios for dying stars. Red dwarfs are really small, low mass stars, and these are the most common stars out there. Believe it or not, the most common stars are red dwarfs. Now, the reason we don't see a lot of them in the night sky is because they're not as luminous. They're small, they're low mass, low temperature stars, so they're not putting out a lot of light. So it's very hard to see these stars. So we're hoping that we get better equipment and are able to see more of these common stars. Then we have these blue supergiants. These are really high mass stars. Sometimes there's a big clump of gas that gravity acts on, and that results in this very large star being born. And we'll see large stars burn through their fuel very quickly. But of course, if they're large and they're high mass, they're going to be very luminous, and they have a faster evolution. So we'll look at their evolutionary lines. And then we have the term called neutron star that comes up. Neutron star we'll see is the collapsed core of a high mass star. And we'll come back to this, and then we'll also look at stellar black holes, which are collapsed remnants of stars as well. Okay, so some of the terms that come up right away, I want you to be familiar with. So these terms, it's important to know what white dwarfs are because they're on this HR diagram, and this will give you an idea of how we classify these. So here we have this diagram that's been used since the 1900s to classify stars and show these relationships between the surface temperature, luminosity, and size of stars. Okay, so most of the lifetime of a star is in this main sequence right here. Here's our main sequence. Okay, and here's our sun right in the middle. Okay, so what happens is a star is born and it moves into this main sequence when it starts its fusion process, and the majority of its life is going to be spent there. So you can start to see some of these trends here. You see the spectral classification we're talking about as far as temperature. So here you have O, then you have B stars from 10,000. Here's a better way to do the range of numbers. You could say 30,000 and above is O. From 10,000 to about 30,000 are B stars. And then we have our A stars, F stars, G stars, K stars, M stars. Okay, so M stars being the lowest temperature. So decreasing temperature is really, really dim stars. So we have the spectral type. So here we have temperature plotted on this horizontal axis, which is what your spectral type is based on. And then we have our vertical axis, which is the luminosity. So, you know, here it's in terms of solar units. So it's in comparison to the sun being 1 unit. So that's 1 solar luminosities. So something that's up here is going to be 10 times as luminous as the sun. Something up here will be 100 times more luminous than the sun. So Vega is almost 100 times more luminous than the sun. And then something up here will be about 1,000 times, etc. Here, this will be like 1/10 the luminosity of the sun. So this is a luminosity in comparison to the sun. And remember, that's in so many watts per meter squared. So important to understand that. So here we have our luminosity plotted against temperature. So here you could see the categories. And well, these classifications kind of vary because they've been modernized a lot. There's still a lot of old textbooks that have different sort of categories for the giants and the supergiants. But right along here is our main sequence strips. And then here we have our white dwarfs. Okay, these are dead star embers. The Sirius system is contains a white dwarf. So Sirius B is actually a white dwarf. And then Sirius A and B orbit around their center of mass. So on this side we have giants right here. So here are some red giants. These are Pollux is part of the Gemini constellation. Arcturus is in the night sky, so we could see some of these. But you can see Antares, Betelgeuse, that's going to come up. We're going to see that a lot more in the fall when it's really visible in the evenings in the Orion constellation. But there's Betelgeuse right here. Oh, it's only 3,700 degree Kelvin, but it's huge. It's a supergiant. Okay, and we have some others on there. So we also have blue supergiants. So these must be hotter temperatures, you could tell. Okay, they're on this side of the scale. So we have different categories. So our giants are in separate categories. And what we're going to see as you run out of fuel, the sun's going to pop into this giant phase. If you're one of these guys, you might go into the supergiant phase. So the sun eventually is going to pop into this giant phase. And then when it gets rid of its atmosphere and its outer shells, it'll pop into this white dwarf stage. So that's the future of our sun, but we're talking billions of years still. Okay, so some more emphasis here, some more clarification on these categories. And so some of these have been updated. Like we also have this new category that's been added called hypergiants. So here's our supergiants. We also have bright giants, subgiants, giants. So you have a lot of different categories for giants. So these are some of the older terms that have been used. And we have this category of our main sequence. And then right down here on the verge of being a star are brown dwarfs. Okay. So we think that there's a lot more. They're just very hard to find, brown dwarfs, because they're very, they're not putting out as many photons for us to detect. But the interesting thing with brown dwarfs is that they have all the features of stars. They just don't burn hydrogen the same way. They fuse something called deuterium, but we also notice that they're always the center of planetary systems. So they act like stars. Okay, so again, going through these different classes. So we have all our spectral types. O star's hottest, M star's coolest. The sun is a G star. Now we also have subclasses of these that are used with numbers where the higher numbers are hotter. So the sun is a G2 star, which means it's hotter than a G1 star. So you have these different temperature ranges for stars. So sometimes we'll classify a star as like a K5 star or a K2 star, M5 or M2 star, etc. So here we also have the vertical axis where we have supergiants, bright giants, giants, subgiants, main sequence. So based on the historical one, we have these subgroups. So the sun is a G2 Roman numeral 5 star. So the G is the spectral type. 2 is the subclass, telling you it's hotter than a G1 star or it's cooler than a G3 star. And this Roman numeral 5 right here tells you it's a main sequence star. It's not one of the other categories. So again, just some relationships as you increase radius, surface area, and temperature, it will be more luminous. And then it'll change its position, right? So if you increase the radius, you're going to go up in luminosity. Okay, so some other relationships. We have this other relationship for main sequence stars, and it's between the mass and luminosity. So if you're a main sequence star, which is the majority of the stars, what we know is that your luminosity increases a lot significantly by your mass. So if you put the mass of the star in there and put it to the 3.5 power, it'll tell you how much more luminous it will be. So this is the mass in solar units compared to the sun. So a star with 3 times the mass of the sun can be predicted to have a luminosity of 3 to the 3.5 power, which is about 47 times more luminous than the sun. Okay, that shows you how that works for main sequence stars. Okay, I'm going to do a quick little outline, and then I'll just take some questions, and then I'm going to highlight this starburst real quick. And then what we'll do tomorrow is we'll work on a few more details as far as the evolution of the stars go and the dying parts of stars. Okay, so just to highlight the main process a star undergoes. So what we all do is we start with this cold molecular cloud, right? And then we have a shock wave. So the interesting thing about stars is it's like a dying star triggers new stars to be born, right? So we have these clumps of gas and dust just out in pockets of the galaxies, the different galaxies. And we'll see when we look at our own galaxy that we have certain areas that have pockets of gas and dust. And that's where the star forming regions are. And there is hypothesis that we're running out of these star forming regions, which means that we'll be running out of stars to make. Not for a while yet, but we have these pockets of gas, and that's what leads to the actual star making process. Then we go from protostar to T-Tauri star, and then we jump to this nuclear fusion stage. And this is where we're going to live our life as a main sequence, right? So we're going to go through this fusion stage, or nuclear reactions in general. We'll see that's going to depend upon the type of star, the mass of the star. And then eventually you run out of fuel, and then the star goes through this dying process. So if you were to pinpoint the main outline of the lifetime of a star, it's just, it's forming out of the gas cloud, starting the fusion, running out of the fuel, and then dying. Now, this process, going from these stages, the amount of time is going to depend upon your mass at all different points. So big stars, we're going to go through this whole process really quickly. They're made, they burn up their fuel really quickly, and then they die quickly, and that's it. But we'll see low mass stars actually can exist for a long millions and millions and millions of years, billions of years, I should say. A medium-sized star like our sun, we're looking at about a 10 billion year lifetime from birth to death. Okay, we're halfway through, so we're still in this nuclear fusion. So we still have 4 to 5 billion years before we start really do our dying process. Okay, so some hundreds of billion years, I should say tens to hundreds of billions of years for small stars, about 10 billion years is the average for medium stars, and much, much less than that for very large stars. Okay, and we're going to get back, we're going to do more of this tomorrow. We'll look at the nuclear fusion, the proton-proton chain, and the C&O cycle, so you can look that up. We talked a little bit about hydrostatic equilibrium, but I have some diagrams I'll bring in. And these will be important concepts when we look at how stars evolve and begin to die, which is what we want to say for tomorrow. So a real quick tour through where stars are born. I heard somebody had this as their screensaver. These are the popular images from Hubble especially. So where are stars born? Well, nebula. So we know nebula stems from the term cloud. And we have different types. We have emission, reflection, and dark or diffuse. So you might want to go back to the spectra slides to review that if you don't remember the 3 different types. So there's all kinds of recycling going on. Here's a typical star forming region. Okay, and we can see this in optical light. Then the Carina Nebula, this is emitting light, and we call it a star forming region because there's excitation going on. So this is being heated up in the process. The gases are being heated up. So they're emitting they're emitting certain spectra wavelengths defined by those gases. We see emission spectra. And here's the Carina Nebula. And this is in the Sagittarius arm of the Milky Way. So we'll see where that is when we study more of the galaxy. So this is 7,500 light years from Earth. And we're looking at this in X-ray. So we have about 14,000 stars in this region. That's really a lot of stars packed in there that are being born. And you'll typically see that stars are born together. So we're still trying to figure out the siblings to our own sun. A whole group of stars were born together with our sun. And when we look at these clusters of stars that are born together, we see a lot of similar processes, and we can analyze them because some clumps are bigger than others, and some lead to higher mass star evolutions, and some are lower mass star evolutions. But there's a lot of pieces that help us puzzle out star evolution in general when we look at these clusters of stars forming together, because we can make good comparisons. So they typically ignite together. So one star ignites and there's a shock wave, and another star ignites. It's sort of like popcorn, popcorn in the nebula. That's the way I always thought about it. So I don't know if that helps. Okay, so here's the Eagle Nebula, a famous nebula that has all these star forming regions. So we could tell by the light it gives off. Optical light is really high frequency light. And then we could see, here's the optical light. And then we have the infrared light. You could see where the heat is just being given off. Okay, so these are, this is in the heart of M16. M16 is a Messier object, Messier objects. They're these objects that astronomers like to identify in the night sky that are not just planets or stars. So there's a lot of interesting things to look at in the night sky, like star clusters, different types of nebula, center of a galaxy. So this is one of those interesting night sky observation objects to try to look at with a telescope or binoculars. So this is called the Pillars of Creation. So this is from the Hubble image. And so here we have all these star forming regions and these wispy clouds. So there's tons of gas and dust, and it's just packed full of stars being born. So the blue stars in the image are representing oxygen, red is sulfur, and green represents nitrogen and hydrogen. Now most stars are composed of hydrogen because that's what the majority, that's the most abundant element in our entire cosmos, in our universe. So, but there are traces of other elements, like our sun, when our sun was born, got some of the remnants from the exploding star that triggered the shock wave that was responsible for the shock wave that triggered our star's formation. So we had some heavy elements in that little cloud of gas and dust as well. So here, these colors are telling us what is also residing inside these pillars. Okay, so ultraviolet light will give us the information on the high energy produced from these young stars. And this is roughly 4 to 5 light years across. So then we have 70 by 55 light years all around here. And that's a huge distance. It encompasses a big distance. Okay, so it's always fun to look at these in different types of light, optical and infrared. And this is what we're going to head to tomorrow. So I just kind of give you a heads up on what we're going to look at. The big thing is how you're going to live your life as a star. And we're going to look at the process involved, like, you know, how you're making your fuel and holding yourself up against gravity. So we have different evolutionary lines. So here we have our protostar. We should insert a T-Tauri star here. And then you go on, if you're a brown dwarf, you're just going to cool off. You're not really burning fuel. You just slowly diminish. But the main 3 lines of evolution we want to look at is the evolution of a low mass star, like a red dwarf, the evolution of a medium-sized star, like the sun, and then the evolution of a high mass star, like a blue supergiant. So a low mass star will live a long time and just burn its fuel. A medium mass star, like our sun, will eventually run out, become a red giant, expel a planetary nebula, then turn into a white dwarf. A very large mass star will end up burning through its fuel quickly exploding as a supernova and then become either end up as a black hole or a neutron star. So we'll look at the scenarios of what your death will be, what your end game will be as a star. So some other interesting questions, interesting ideas that come up as far as stars go is going back to the nebula, is the clumps that you're making out of will kind of dictate how much mass you're going to have. So the mass at the beginning and the mass at the end will tell you how you're going to live your life as a star. And we're trying to understand some of the earliest types of stars from since the Big Bang. So the first type of stars we're still trying to find evidence of. So they typically were much larger stars, and they didn't last as long. So we have something called population 1, population 2, and population 3 stars. And the types of stars have different types of element abundances. Like the earliest stars were really did not have a lot of the heavier metals inside them or elements. So it really took a few generations of stars to get to be the way they are now, to generate the heavy elements and metals that we use, that we see, here on Earth or in other planets. So those are rare substances in the cosmos. As we know that gases are really prevalent, like hydrogen and helium, etc. But to get those heavy metals, that really took a long line of stars before us to get to this point in evolution as far as stars go. So anyways, I'll stop there and we'll